Hello, in this video we're going to be looking at what is a buffer and what does it mean to be a buffer, and then what is a buffer made out of. And so we're going to watch a little video demonstration here that I recorded, and just to explain to you what we've got here. On the left hand side we've got a beaker that has water in it. The reason it's yellowish though is because I've added an indicator which is called bromothiamol blue, and that indicator, or any indicator, is something that changes color based on whatever pH is present. And so different indicators change colors to different colors at different pHs. This particular one changes from yellow in an acidic pH range to blue in a basic pH range. And so again, that's why the beaker on the left here, which is just pure water with some indicator, it's actually so it's coming up yellow, but I think the pH changeover point somewhere around 6 or 7. So you know it's in that range roughly of again, it's on the lower pH end for this indicator. On the right hand side we've got a buffer, and what the buffer is, in this case the buffering component is coming from the antacid tablets that you can see there in the screen. And again, the color here is, well, if you notice, if our indicator changes between yellow and blue, this is kind of, well, it's green, so it's somewhere kind of like right around where the actual pH changes over from the yellow to blue. So that's why we're getting the greenish color. So we're going to watch the addition of some substances. We're going to add some sodium hydroxide and some acid and see what happens as a result. And how it's different for the water versus the buffer solution. And I'm going to fast forward here to what we're looking for. Oops, go back. Alright, so what we're going to add in is sodium hydroxide, that's NaOH. And so in the water beaker, as we add it in, mix it up so it gets distributed, we see that it turns from yellow to blue. So that color indication tells me that the pH has gone up, and that makes sense because if we add hydroxide, we know that that will increase hydroxide ion concentration. Conversely, the H+ concentration decreases, and that means the pH went up, and it must be up high enough to be into the blue range. So our water basically turns basic because we increased the hydroxide ion concentration. For the buffer solution, so now I'm adding the sodium hydroxide drop by drop. So every time I'm stirring, I'm adding another drop of sodium hydroxide. And you'll notice that that color that it started off as is pretty much remaining. And so you can see I'm dropping in a whole bunch more sodium hydroxide, and eventually I squeeze in a whole bunch more. And so the thing with the buffer that we need to recognize is that the buffer resists changes to pH. And so again, the evidence of that is that the original green color persists, meaning that the pH must have not gone up. Even though we added hydroxide, when we had just pure water, we had added enough hydroxide to make that pH change when we're adding the sodium hydroxide to the buffer, though because of the components in the buffer, it is resisting the pH change. So the next thing we're going to see is what happens if you were to add acid back to the same system. So there's hydrochloric acid. Again, hydrochloric acid will be supplying us with an H+ concentration increase. And so when we drop in the hydrochloric acid, again, the water does not have anything that allows it to resist change to pH. So once I start adding H+, the pH is going down. And then we see it go into the acidic range that makes it turn yellow. Again, I can add hydrochloric acid to the buffer, and same thing happens, which is pretty much nothing, because the buffer is able to counteract the addition of that acid. So, what is a buffer exactly? Well, let's take a look at some notes then. So, the buffer, how is it able to do that? So, again, the buffer solution, it's made out of a weak acid and its conjugate base, and because of that weak acid conjugate base pair, it's able to neutralize small amounts of acid and bases that are added. There is going to be a max capacity to how much you can add. We call that buffer capacity. So, you know, it's not like I could dump in endless amounts of acid or base and see no change. The pH is probably changing a little bit, but as you could see from the indicator, it wasn't changing enough to get us into a completely different pH range. So it might change, you know, 0.01, 0.02, and so forth, depending on the concentration and the amount of acid or base you add. So a buffer solution, what it does is it resists changes to pH that would otherwise be caused by the addition of acids or bases. So like we saw in the beaker of pure water, that does not resist pH changes. So if I increase H+, pH goes down. For a neutral substance, that's what we observed with the water. When I added hydroxide, pH goes up. You know, a substance that does not contain buffering components, this conjugate acid or weak acid-base conjugate pair, if it doesn't contain that, it's not going to be resisting the change to pH like we saw with the water. All right, so let's look at the reactions that are going on in a buffer that allow it to resist changes to pH. So when we add an H+, so we add an acid, the weak base is available to react with the acid that we're adding. So again, the weak base, well, we said it's a conjugate acid-base pair. So let's pretend that our weak acid is HX, so it's just a generic anion, and then X minus being the conjugate base, right? It has one fewer H+, one less H+ than the weak acid. So if I'm adding an acid, this X minus, this anion, this weak base component is present and will attach itself to the H+. So this is the reaction that we'll see when we have an acid added to the buffer system. Now again, we already have HX, so we already have the weak acid present because we said that a buffer contains both the weak acid and its conjugate base. But again, we're just focusing on the components that are doing the reacting when we add the acid. So the hydrogen that's added, it is attached to the anion from the weak base, and as a result we'll see a little bit of an increase in the weak acid concentration. But again, we don't have as much free H+ in solution as we would have if it wasn't able to attach itself to the anion of the weak base. So likewise, when we have the base added, the weak acid is reacting with the hydroxide ion, which is the base that we're adding, and the weak acid is going to transfer its H+ to the hydroxide ion. So we see the hydroxide acting like the Bronsted-Lowry base, the HX, the weak acid, acting like the Bronsted-Lowry acid. So then we have water, and then we end up with an increase in the weak conjugate base. And so again, it's because of this balance between, so like this is all just one big mixture of a system, and we have this balance between H+ and, or sorry, between the weak acid and its conjugate base. So in this example, again, it's X minus and HX is the acid-base pair. But because there's the weak base available to attract and attach and remove the H+ from solution, we see the pH go down minimally as a result of adding an acid in the buffer solution, because there's that weak base there to react with it. And similarly, when we add hydroxide, normally that hydroxide would make the pH go up, but because there's the weak acid available to react with it, that minimizes how much hydroxide, extra hydroxide, ends up being present as a result of the addition of that base. And so then we end up with, again, a little bit more of the conjugate base being formed, but not nearly as much hydroxide remaining in solution in addition to what we started with. So I'm going to show you one additional little demonstration here, and we will see if we can make a prediction here. Okay, so this is, first of all, just to show you, it's an universal indicator in water, just to show you what a universal indicator is. If you think about pH paper, so this is like the pH paper roll. Although this is not exactly the same stuff. It's kind of the same idea that pH paper can change a bunch of different colors depending on the actual H+ concentration and therefore the pH. So right now, like this greenish color usually means you're around 7. You know, on this particular pH paper, it more indicates a pH of around 8. But anyway, it's like fairly, you know, kind of in the neutral range for what we're seeing now. So similar to what we saw in the other demo, we're going to see color change when the pH changes. So for this one though, there's just more colors than the 2 colors that we saw with the other indicator. Okay, so notice like the reddish colors, those are indicating lower pHs, and then the bluish and purple colors, those indicate higher pHs. So that's something to make note of. Okay, so we're going to start with adding hydrochloric acid. And so I want you to think about for a second, if I add hydrochloric acid, what's that going to do to my pH? And so notice it turns it yellow. And it goes back to green a little bit. Still pretty yellow though. And then we see a little bit of orange. And stir it some more, and now it's kind of turning that pinkish reddish color. So I'm adding hydrochloric acid, and the more H+ you add, the lower the pH gets. So that's something we should understand moving forward. And so again, see the orangish color, reddish color indicating that the pH went down, which makes sense. You add an acid that's more H+, and that lowers pH. So now we're going to try sodium hydroxide. So again, if I think about what does sodium hydroxide do, well, that contains hydroxide. If I increase hydroxide, I'm lowering H+, and that would mean the pH goes up. So watch what happens. There's 1 drop, and we see it kind of start to go back a little bit to the orangish color, and then it gets to like the yellowish color, which indicates the pH is going up. And again, pH goes up because hydroxide ions going up and H+ is decreasing. And so now we're kind of in the blue-green range, and now it's going all the way to purple. Okay, so that demonstrates to you what the universal indicator does. So it indicates pH based on color. And so in this next little demonstration then, we're going to look at 2 beakers. I cannot remember which one I had the buffer in. One of them is contains a buffer that has a pH of 7. So there's a conjugate acid-base pair in roughly equal amounts. And in the other beaker, it's just water. And both of them have the universal indicator in them. So I put 1 drop into each of sodium hydroxide. Again, you notice sodium hydroxide made the pH go up for the one on the right. And let's watch what happens with the hydrochloric acid. And so again, the substance on the right, or the beaker on the right, the color changes indicating a pH change. The one on the left though, color stayed green the whole time. And so that green color not changing tells me that pH hasn't changed. So if you had to guess which one is the buffer, the answer should hopefully be the one on the left, right? Because the color didn't change, indicating the pH didn't change. So again, there's a weak acid, weak acid, and its conjugate base present. That weak acid is available to react with any added hydroxide to reduce its impact on the pH. And likewise, there is a weak base present to react with any added acid, any added H+, that again reduces the impact of the H+ presence on pH. And so that is what buffers are all about. So buffers resist changes to pH. They contain a weak acid and its conjugate base, and they're roughly in equal proportions for most buffers.